I just want to sort of recap what we were doing last time. Remember we watched John got and try the straw thing? We like tried to suck out liquid from the straw and watch the story stuff. Well, a straw is a lot like a manometer. So a straw works very much the same way as a manometer. So I just want to emphasize that. Erase this. That is, it's not really you pulling up fluid in the straw, but instead it's what? What is actually pushing the fluid up into your mouth? Air pressure, right? The atmospheric pressure. So, you know, you have this, like you have a cup with a straw, the air pressure is pushing down onto the liquid, and you create a slight vacuum inside of your mouth, and that pushes it up into your mouth. So you create a pressure that's less than what was in your mouth, and that's very much the same way that a manometer works. Remember we had this picture of a manometer where we have a liquid over here, and we have a pressure here, and then we have a another pressure over here. And you can imagine that this is like your mouth. Let's see if I can draw a mouth. That doesn't look anything like a mouth, but that's a person's mouth on a straw. Y'all see it a little bit? No. Anyway, this is a person's mouth, and inside of your mouth you create this slightly lower pressure than the atmospheric pressure, and it pushes down in this, pushes down and pushes that fluid up into your mouth. Now to measure atmospheric pressure, we talked about this, the barometer, which is a special case of the manometer. And in atmospheric pressure, you have this tube that's turned upside down inside of this liquid, and the atmospheric pressure pushes that fluid up into this tube, and this pressure in a barometer is equal to what? We call this P naught. What is it equal to? For a barometer, special case of manometer, it's equal to 0. So there you have a vacuum. Now, if your fluid, this pressure, by the way, is equal to rho GH, the density of the fluid times the acceleration due to gravity times the height of this column. And if this fluid is, I don't know, mercury, how high is this column? What is the height of mercury at 1 atmosphere? Right, 760 millimeters of mercury, or 764, which is the same as a millimeter of mercury. So that's where that comes from. This measurement is in millimeters of mercury, and it's the height. You have 1 atmosphere of pressure and 0 pressure inside the tube for a barometer. Okay, now what if you replace this with water? What is the height of this column? Now remember, I sort of mentioned it last time, and the guy mentioned it on the video. If instead of using mercury, you use water, which is more or less dense than mercury. It's a lot less dense, right? It's actually a lot less dense by a factor of 10. So it's 1/10 the density. Oh wait, no, that's not true. It's actually more than a 10, but almost a factor of 10. Right? So how high is that column of water if you use water in your barometer instead of mercury? You remember how high it was? He said there was like this theoretical limit to the length of a straw that you can have. I remember. Yeah, about 10 meters, so which is 30 to 40 feet. So 10.3 meters actually. So if I replace this with water, let me just sort of recap. So with mercury, Hg, the height is equal to 760 millimeters at sea level. That's at 1 atmosphere. With water, on the other hand, the height equals 10.3 meters with the pressure equal to 1 atmosphere. That's at sea level. All right. So that's where this theoretical limit for the length of a straw comes from. That if you have a straw that's 10.3 meters or longer than 10.3 meters, it won't work. Just simply because the atmospheric pressure isn't strong enough to push that liquid up to 10.3 meters. In fact, you would have to create a pressure that's less than a vacuum, and you can't do that. Okay? So that's where this theoretical limit, and that's what he was talking about with the whole thing about the straw and how long it is and all that business is. That straw can't exceed 10.3 meters. It's kind of a cool science fair project, actually. Like if you know a middle schooler or a high school student that wants a science fair project, they could do some study of what is the maximum they can get a straw to work. I think that would be kind of fun. Y'all know any kids like that? They're doing science fair? No? Okay. Well, maybe it could be interesting. Let's do a few questions, sort of recapping what we did last week. Oh, did I tell you the oxygen magnesium joke? It's relevant. I did tell you that. Oh, that was a good one, wasn't it? Wish I could tell it again. Don't worry, I have more. Let's see. So let's do these questions anyway. So to just sort of recap from last week, these are actually some from old quizzes and exams and stuff. This figure shows a pressure measuring device. A dense fluid fills the gray shaded area. You might not be able to see that. Let me show you. I'm going to draw it in. This gray shaded area, which is now blue, looks like that. Which of these best characterizes the relationship between pressure P1 and P2? This is P1, this is P2. P1 is less than, greater than, or equal to P2, or is P1 equal to 0? That is, P1 a vacuum? Is P1 less, greater, equal than P2, or is it equal to 0? See, you're doing pretty well. I'm going to take this away at 128. 128. Very good. B is the right answer. P1 is bigger, just simply because the level of this pressure, or level of this fluid, is lower than the level here. All right, and if we were to calculate P1, we would take the density of the fluid times G, which is equal to 10, times this height. That's that rho GH. You descend below the surface of the water. As you go deeper, the pressure increases. Is A that a true statement, or is that a false statement? All right, just a few more seconds. I'm going to stop at 42. 42. Listen, y'all got it all right? This is like a really easy question, so I'm going to save. I have a good joke for you for later, like when you do well on a hard question. This is a really easy question. All right, I just want to warn you. That's good though. Let's try this though. So instead of this, let's say, how deep must you descend in order to reach a pressure of 1 atmosphere? So how deep must you descend in order to reach a pressure of 1 atmosphere? I'm going to give you some options here. Is it, I don't know, 1 meter, 10 meters, 100 meters, or 1,000 meters? How deep must you descend in order to reach a pressure that's equivalent to 1 atmosphere? You should know the answer to this if you think about it. How deep must you descend in order to reach a pressure of 1 atmosphere? Okay, not doing real great right now, but think about the straw. Okay, think about the straw. What is the pressure pushing on the liquid to push the liquid up into the straw? Or what is that pressure? We've already answered that one. What is it? It was atmospheric pressure, right? It's 1 atmosphere. That's what pushes it up into your mouth. Right, so think about that. And maybe that'll help you with this question. You can ask your neighbor what they think. Right. Please do ask your neighbor what they think. Or tell your neighbor what you think. Something. All right, I'm going to stop at 125. It looks like we're rounding up to the right answer. 125. B is the right answer. Very good. A lot of you had 100 meters, but you only have to go about 30 feet in order to reach 1 atmosphere. So in scuba diving, they teach you that, right? I'm not a scuba diver, but my brother is. No scuba divers, right? Yeah, like you are every, how many feet to 1 atmosphere? No, it's 33 feet. Don't listen. I'm pretty sure it's 30 feet. It could be that if you have different densities of water, that could be the case. So I don't know how different the saltwater density is. Okay. Well, yeah, so I think that actually the density of water does change a little bit when you go deeper. That might be the difference. I'm pretty sure it's 30. But that might be fresh water. Salt water is more dense. That's why you float better in salt water, right? Because it's more dense. We'll talk about that later. Yeah, it was better when I didn't think about it. So now you're calling it. But it's the same idea as this straw, right? That if I have this straw, the limit is if I have a barometer, rather, that's filled with water. You know, if I have 1 atmosphere of pressure here, then I have 30 feet roughly, or 10 meters of liquid there. So this height, this column of 30 feet gives me 1 atmosphere. Similarly, the same idea is true, is that if I'm submerged in a liquid at some point, that is 10 meters or 30 feet below the surface, then my pressure here is also 1 atmosphere. Does that make a lick of sense to you? Sort of, kind of? You need to know barometers and manometers. That stuff is in your book as well, and also this idea of pressure at a depth. We'll come back to it later. We'll answer some more questions in just a bit. Let's try a different question. Which of these is not a unit for pressure? Newtons per meter, millimeters of mercury, a bar, or a Pascal? All right, I'll stop at 35. 35. Most of you have the right answer. Well, sort of. All right, A is the right answer. What could be changed in A to make it correct? It could be what, Luana? 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 How could A be made correct? You said it. Yeah, I think so. Did you not say it? Who else said it? Newtons per meter what? Make it squared, right? So A is not newtons per meter. It should be newtons per square meter squared. All right, what is the absolute pressure in water at a depth of 5 meters? And I give you the density of water, there's the acceleration due to gravity, and then the atmospheric pressure. This was from an old test, I think, last semester. I'm going to stop at 1:30. 1:30. Oh, nice. Okay, so the two most popular answers, only one of them is correct. I'm going to mark it correct, but D is almost correct. And you probably sort of missed that we talked about last time. Now, if we have pressure that is due to the weight of a liquid, right? So if I have some liquid and I take some point down inside of the liquid, there's a pressure felt there. Like the bottle when the guy was descending, there was a pressure that was pushing in on the sides of it. And it's related to the height of this column of water that sits above that point. And we can figure out that pressure is equal to rho times G times H. And if you put D, that's probably what you did, right? Yeah? All right, so you said rho is, what was rho? 1,000 kilograms per cubic meter times G, which is 10 meters per second squared, times H, which is 5 meters, which is 50,000 newtons per square meter. All right, but that's not the right answer. Those of you that put B, on the other hand, included what? What did you include in order to get that 150,000? The atmosphere. So you also have the atmosphere, which is pushing down onto the surface of the water, or the liquid, or whatever happens. This is water. So I have an atmospheric pressure. 1 atmosphere is 100,000 newtons per square meter. Right? We have this horrendous amount of fluid that's sitting on top of our heads, and it's pushing on us with 100,000 newtons per square meter. And of course, you all went out and did the newspaper thing for all your friends, right? Right? Yes. So to demonstrate that really extreme pressure. And so we want to add this, actually, to our pressure due to that height. So we're going to add the second term plus P naught. P naught, that's plus 100,000, which gives us 150,000, which is the right answer. B is the right answer. All right, just a couple more, I think. Okay, one of the possible sources of pressure includes internal forces due to interaction of molecules. Is that A, true or false? We have 3 sources of pressure, all right? Is one of those the internal forces due to interactions of molecules? True or false? A, true or B, false? I'm going to stop at 42 seconds. 42. Excellent. Let's do one more. So what, do y'all remember the other 2 sources? Interaction of molecules, that's where we get the ideal gas law. We'll get into that today. What are the other 2 sources of pressure? Weight of the fluid and an external force, right? So we'll get into both of those today. The weight of the fluid, or excuse me, the external force, and this one, ideal gas law. Oh, that's the end. All right, so this pony walks into a bar, and he goes to the bartender. He says, "Bartender, give me a drink." And the bartender says, "What?" And the pony says, "Come on, bartender, give me a drink." And the bartender says, "Huh?" And then the pony says, "Come on, give me a drink." And the bartender says, "What? I can't hear you." And then the pony says, Oh, I'm sorry. I'm just a little hoarse. Took a second, huh? Yeah. All right. All right, folks. Let's look at the pressure due to an external force, and here we're going to introduce Pascal's principle. Pascal's principle is sort of a generic principle that says that whenever you apply a force to a fluid, or whenever you apply a pressure to a fluid, that pressure is felt all the way throughout the fluid. So if I had a long pipe that was filled with a fluid, and I pushed on this end, then I would feel a change in pressure throughout that fluid. That would be the same all the way throughout. Now, I say fluid, but it actually assumes, this idea assumes what about a fluid? What has to be true about a fluid in order for me to push on it? I feel that change in pressure all the way throughout the fluid. Remember, fluids include liquids and gases. For which of those would that be true, this idea of Pascal's principle? Both of them? Only liquids or only gases? Okay, imagine if I have a gas. All right, look, I have this room of gas. And I can change the pressure of the gas around my hand. Watch. You'll see that? Like I changed the pressure. Did you feel that? No, you didn't feel it, right? Because as I do that, I change the pressure, but it's not felt all the way throughout the room and all the way throughout the container. However, if you have something that's filled with an incompressible fluid, like water, for example, like hydraulic fluid, if you have a change in pressure at one point in the fluid, then you have a change in pressure all the way throughout, because that fluid is not compressible, it's incompressible. Let me write that down in words. So let's see, Pascal's principle. Well, first of all, this is pressure due to an external force. There we have three sources of pressure: pressure due to the weight of a fluid, pressure due to an external force, and then also pressure due to the interaction of molecules. That comes about because of an increase in temperature. So pressure due to an external force, Pascal's principle says that when pressure is applied to a fluid in a closed container, actually, when pressure is applied to an incompressible fluid, that change in pressure is felt throughout the container. Let me draw you a picture. So say, for example, I have this container that's filled with an incompressible fluid, which is really just a fancy way of saying liquids, because all gases are compressible. All gases, if you take them in a container and you make it smaller, you can compress them. But if you put most liquids are incompressible, like water, for example, is pretty darn incompressible. Oil, most liquids are incompressible. Practically all liquids are incompressible. If you put a liquid in a container and you try to make it smaller, it ain't happening, right? It just doesn't get smaller. It's incompressible. You cannot compress a liquid, but you can compress a gas. All right, so let's say that I have this container and I have a piston and I apply a certain force over a certain area, and it causes a change in pressure that's equal to that force over that area. This thing is filled with a liquid. All the way throughout this liquid, I feel a change in pressure that is equal to the change in pressure that is given to me by the piston. I feel that change in pressure there. I feel it right there. I feel it there. I feel it all along the sides of the container. I feel it everywhere. That's what Pascal's principle says, is that if I have a pressure applied to a fluid, then that pressure is felt all the way throughout. Okay. Let me show you a good application of this is a hydraulic lift. You ever used a hydraulic lift? Right, you have a little, well, most of you probably have a screw type jack in your car, but in some cars you actually have a hydraulic jack. And if you go to, to the mechanic or whatever, those big jacks that they pull out and they lift your car, or if you're trying to lift a person, often you'll have a hydraulic lift. Or if you go to the barber shop, they use the chair and they have a little thing that lifts you up. Those are all hydraulic systems, and the way they work is they utilize this Pascal's principle, where they have a closed container with two different pistons. I have one piston over here and one piston over here. Now this piston, you put in a force, I'll call this Fn, and this piston, I get an output force. This system is filled with a liquid, usually what? In a hydraulic system. What is it? It's usually filled with oil. Why would you use oil for a hydraulic system? Why not use water? Water is a lot cheaper. It's not toxic like oil is. It doesn't make a mess. So, and we also, water is compressible just like oil. Very much the same property. So why would you use water or oil instead of water for these hydraulic systems? Well, it's in a closed container, so that's not really an issue. Lubrication. Huh? Lubrication. Okay, yeah, lubrication, and then also just rust, so it's sort of a practical thing. All right, so anyway, I'm filled with this fluid. Pascal's principle says that whatever change in pressure I feel over here, I'm also going to feel over here. So we can say then that Fn over the area of that input piston is equal to F out over the area of that output piston. Which force is going to be bigger? I put in a force over here, and I get out a force over here. Is Fn going to be bigger, smaller, or equal to F out? Let's do that as a clicker question. So, is Fn, is it A, Fn is bigger than F out? B, Fn is equal to F out? Or C, Fn is less than F out? That is, which force, how are the forces compared? Is Fn bigger than F out, Fn is equal to F out, or Fn is less than F out? By this principle. And notice as I've drawn, I haven't mentioned this, but the areas here are starkly different. The areas here might be a factor of 10, 100, or more difference between the area of the input piston and the area of the output piston. If you just sort of think about how this works in practice, you might get it. But you can also look at this relationship. All right, ask your neighbor. We're not doing real great right now, but ask the 5 or 6 people that have it right now. And just sort of talk amongst yourselves. Let me explain what these answers mean. I'm not sure you're getting it. So here, this is saying that this force, Fn, that is the force you're putting in here, that you're putting in a big force and you're getting out a small force. That's what this first thing is saying. This one is saying you put in a force and you get out exactly the same force. And this one is saying you put in a small force and you get out a big force. That's what those three answers are saying. All right, I'll stop at 2 minutes. 2 minutes, 5 more seconds. Remember, just guess if you don't know. Remember, you do get credit whether you get it right or wrong. All right. So, with a car jack, ever since you looked at a car jack, there's a little piston where you have a big handle and it's attached to a little piston. It's a little bitty thing, right? But if you look down further where it actually moves the arm, you get a bigger piston. So you get a little piston and then you get a bigger piston. Which of the forces is bigger? The force that I put in with the handle or the force that I get out lifting the car? What now? The force out, right. Lifting the car requires a lot more force than moving that handle up and down. That handle almost moves itself. And the reason it is because I have a little bitty area right here. So this number is really, really small. So this number can also be really small. And this ratio will be the same as this ratio. But I got a really big area and I got a big force out. So like the barber chair, like the car jack, like the hydraulic lift of any sort, I put in a little bitty force and I get out a really big force. What's the right answer here? C is the right answer. Okay. We see Pascal's principle elsewhere. So for example, like when your heart pumps, your book goes into this sum. So when the heart pumps, it causes an increase in pressure. And because your blood is incompressible, and it works in this way, Pascal's principle is applied, that pressure is felt all the way throughout the system. So this delta P, this change in pressure, is felt throughout the system. I just realized y'all might not know what this symbol means. Have y'all seen this before? I've been using it a lot. You know what this means? It's a delta, the Greek letter delta, and it generally means a change in something. We'll use it a lot throughout the semester. So here I'm talking about a change in pressure. This means it was something and now it's something else. It's a change in something. The final minus the initial. If you have a baby pushes on your bladder, like if you're pregnant, I mean, I've never been pregnant, obviously. But if you have a baby that pushes on your bladder, that causes a change in pressure in your bladder, and that's what makes you have to go, pee or whatever. All right, so baby pushes on the bladder. Causes a change in pressure. And that change in pressure is felt all the way throughout the bladder. All right, we have 3 different types of pressures. Actually, let's talk about this first. Can I go down? My dad worked at a tire shop, and so like when I was a kid, my brothers and I, we all worked there, like starting from when we were like this tall. And so I like tire things. Y'all like tire things? Yeah. All right. If you imagine a tire, and you have it inflated to 35 psi or pounds per square inch. PSI is just a way to measure pressure. Pounds, that's a force per square inch, that's an area. So we use newtons per square meter, but here this is the same, it's just in the British system. PSI. When the tire is flat, the gauge, a pressure gauge, will read how many PSI if the tire's flat? It reads 0 psi. All right. But the air inside the tire is not actually 0. That would be quite a feat, right? That would be a vacuum inside of the tire, and you can do that, but you need special equipment to get it so that our pressure inside the tire is actually 0 psi. And in fact, at 1 atmosphere, that's approximately equivalent to 15 psi. So whenever your tire is flat, then it actually has 15 psi. So next time you have a flat tire, then you can tell them, oh, it's not flat, it's got 15 psi. All right. So that brings us to 3 different pressures that we can talk about. All right, the first is gauge pressure. And gauge pressure is just what the gauge reads. The second one is atmospheric pressure. We've already talked about this. This is the pressure due to the atmosphere. And then the third one, C, is absolute pressure. In that question I gave you before, that was from an old test, but the absolute pressure is the sum of both of these. That's the sum of the gauge and the atmospheric pressure. All right, so let's say that I have this tire with 35 psi. I say that my tire has 35 psi, which is, the recommended pressure for a lot of tires. Which of these is that? Is that talking about the gauge pressure, what the gauge reads? Is that talking about the atmospheric pressure, which is the pressure to the atmosphere? Or is that the absolute pressure, which is the sum of our gauge and atmospheric pressures? Which of those? If I say that my tire has 35 psi, what is that? Which of these is that referring to? My gauge, atmospheric, or absolute pressure, A, B, or C? All right, folks, I'll stop at 105. Just guess if you're not sure. Most of you have gotten it right. You can probably ask your neighbor to tell you the right answer. Very good. A is the right answer. That's your gauge pressure. So that doesn't include your the atmospheric pressure. So if you were really to be correct about it, if you wanted to actually know the pressure inside your tire, it would be 35 plus 15, which would be 50 psi. I have a little video. I just think this is interesting about how they make gauges. It's just a machine shop. It doesn't really have much to do with measuring pressure, but I think it is fairly interesting. Let's watch it. It's just a few minutes long, and then we'll get back to pressures. All right. I'm going to try to pause this. You're measuring pressures. You're really just comparing an unknown value to a known value. So you're comparing some pressure that's unknown to a pressure that's known to cause this tube move in a certain position. And so the same here, anytime you're doing a measurement, you're comparing a known value to an unknown value. And we'll sort of see that come up throughout the semester. We've already seen that already with pressure, right, where we compare the unknown pressure to the height of the column. All right, let's do interaction of molecules. And yeah, it looks like next time we'll get into fluids and motions and Poisson equation, and then we'll start to move into some applications for these various things. So we have three things that cause pressure: the weight of a fluid, right? An external force, like Pascal's principle, and then the third thing that we have is the interaction of molecules. You've probably seen this in high school chemistry, or even physical science. Anytime you have a substance that has a certain temperature, or a gas that has a temperature and a pressure, then it has a certain amount of pressure. This is described by the ideal gas law. So you imagine that you have a container of gas. If you add gas to the container, what happens to the pressure? Does the pressure go up, or does the pressure go down? Okay, I was going to do this a quicker question. If you add gas to a container, you have this container, and you add gas to it, what happens to the pressure? By the way, it's sort of getting to this idea of the ideal gas law, which you've probably seen before. PV equals nRT. And if I'm adding gas to the container, which of these variables am I changing? Which one? Y'all remember ideal gas law? High school, maybe? A number of years ago? Which of these variables, if I'm adding gas to the container, this is my pressure, which of these variables am I changing by adding gas to the container? Small little furry creature, runs around underground, number of something, the number of moles. Which of those variables does that represent? The N, right. So N is the amount. So if I'm increasing N, if I add gas, I want to know what happens to the pressure. Take this away, 111. Very good, A is right. So if I add gas to the container, the pressure goes up. If I raise the temperature, of the gas, what does the pressure do? Does the pressure go up, or B, does the pressure go down? If I increase the pressure, or excuse me, if I increase the temperature of the gas, what happens to the pressure? Does the pressure go up, or does it go down? You probably saw these two laws. You don't need to know this right off. Your book might mention it. These are Charles and Boyle's law. You've heard this before? And then together they make up the ideal gas law. So if I add a container to the gas, the pressure goes up. Now what happens if I raise the temperature of the gas? What happens to the pressure? Does the pressure go up or down? Let me help you out a little bit. So I have an equation here, right? If I do one thing, this equation is always true. It's always true, no matter what I do to any of the variables. So if I change one of the variables, then the other variables have to change in order to make that change the same, all right? So for example, if I increased N by a factor of 2, and everything else was constant except for the pressure, by how much would the pressure have to change? It would have to change by a factor of 2 in order for this equation to still be true. It's an equation, it's equal, right? So if I increase N by a factor of a half, or rather if I decrease it by a half, that means the pressure goes down by a half. All right, so now I'm asking, what happens if I change the temperature? if I increase the temperature, what's happening to the pressure? What must happen to the pressure in order for that equation to still be true? All right, just a few more seconds, 1:45, I'll stop. All right, very good. A is the right answer. It's going to go up. We're going to see sort of relationship type problems like that. Like if I have one variable and I change it, what happens to the other variables as we go throughout? You'll certainly see those on your exam. All right, so as I said, these are Charles and Boyle's law. If I add gas to the container, the pressure goes up. And if I raise the temperature of the gas, the pressure goes up as well. Gives us the ideal gas law, PV. Actually, let me rewrite that. PV equals nRT. P is the pressure. V is the volume. N is the number of moles. It's just the amount of the gas. R is a constant. And T is the temperature. I wouldn't expect any calculation type problems with this because you don't use a calculator on your exam. But I could ask you, like, if I change one variable, what happens to the other? Or I could ask you to identify certain variables. All right, so similar questions to this. Like if I change the number of moles, if I change the amount of the gas, what happens to the pressure, or what happens to the temperature, or whatever. All right, so for example, what if I kept PV constant and I changed N? If I increased N, what would happen to T? Would it go up or down? Up or down? It has to go down, right? So if I keep the pressure and the volume constant, which you can do physically, you just keep those constant. If I increase N, that means the temperature has to go down. All right, so those sort of questions you can see with the ideal gas law. And again, the ideal gas law is related to this interaction of molecules. They actually create this internal pressure. All right. So when you have a gas that is at a constant temperature, then the pressure volume is equal to a constant value. Right. And so this has applications for a lot of things because if this PV is constant, it doesn't change. If I change the volume of something, then it changes the pressure. And if I make the volume bigger, then the pressure goes down. And if I make the volume smaller, then the pressure goes up in order to maintain that PV equal to a constant value. Where is that applicable? Changing the volume of something to change the pressure. In breathing. Right. Thank you, Ronald. Yeah, y'all are all thinking. What happens as I breathe in? What happens to the volume? It's doing what? Getting bigger or smaller? Bigger. So if I make my lungs bigger, y'all make me deep breath. What happens? I lower the pressure. So you're not taking air in and out. You're just changing the shape of your lungs, right? When your lungs get bigger, the volume goes up, and the pressure goes down. And when the pressure inside of your lungs goes down, then that means all the air from the outside rushes in to fill that low pressure area. And when I exhale, I make my lungs smaller, so the volume goes down and the pressure goes up. And then I have a high pressure inside of my lungs, and that forces that air out. Because air always wants to go from high to low pressure. Let me put that into words. So when you're breathing, for example, if you breathe in, right, that means your lungs get big. Is that what a lung looks like, sort of? Not sure. There's two of them, right? All right, so the volume goes up and the pressure goes down because this PV is constant. And when I'm exhaling, the volume goes down and the pressure goes up. So it's sort of correct to say that comes from the ideal gas law. It does, because you have this constant temperature gas that's coming in and out. That's basically a constant temperature. And so this pressure times volume has to always remain the same. Let's see. One more little thing, and then we'll leave off there. I'll give you a quiz. So another 3 or 4 minutes. Pressure in solids. Solids also feel pressure. You know, because they just want to have a life, and parents are always saying, when are you going to get a job? When are you going to get a job? Those solids, they have it hard just like the gases do. They feel lots of pressure. All right. And remember that pressure is force per area, force per unit area. So just like we have in fluids, we also feel this in solids. So say, for example, I have a container here. It has an area equal to 0.5 meters squared. It has a weight of 100 newtons. It exerts a certain amount of pressure onto the surface, and I can calculate that pressure is just 100 newtons over 0.5 square meters. 100 over a half will go into 100. How many times? 200. All right, so it's 200 times. 200 is my pressure as newtons per square meter. And so if I apply pressure to solid objects, then whatever my force is over that unit area is the pressure that's being felt by that solid object. Now that will lead to, that's called a stress. Anytime I have a pressure, this is called a stress. All right, anytime I apply pressure to a solid, that's called a stress. Stresses will always lead to either breakage or deformation of the solid, right, or something we call strain. So stress will lead to strain. The more stress I put on an object, the more strain I will get out of the object. Strain is caused by stress, and stress is the pressure, your force per unit area, and strain is the deformation of the solid. Deformation of the solid. Stress leads to strain. We have something called the elastic limit. Which just says that if you exceed a certain amount of stress on an object, then what's going to happen to that object? If you exceed this elastic limit, it's going to do what? It's going to break, right? So the elastic limit is just that point where you exceed the maximum allowed amount of stress. And then your strain is no longer deformation, it's breakage. So the elastic limit is just the maximum amount of stress before breakage, or when breakage will occur. So your bones, they have an elastic limit. Everything has an elastic limit, right? All right, let's see. So next time we're going to do fluids, and then we'll get into the circulatory system probably next time. All right, we're going to do our quiz right now.